Assalamualaikum and a very good evening everyone. So today we're going to continue with chapter 10, design input and output system to be interfaced with the 68K microprocessor. So at the end of this lesson, you should be able to explain how to interface the 68K with a peripheral input-output device, and you should be able to explain the function of a buffer and latch operation when designing an input and output system. So there are two ways actually to interface a 68K microprocessor with peripheral device. The first is being through the means of a dedicated I/O, and the second is through the memory map I/O. Okay, so in dedicated input-output system, is basically you specified a fixed address in assigning to the I/O device. So meaning that in a dedicated I/O connection, the 68K already have an assigned pin, okay, an assigned pin for you to interface your input-output system to. The drawback of having this dedicated I/O is you need a specific address in order for you to assign the input-output device, and usually require a larger package, and some of the 68K feature will have been abandoned. Whereas in the second way of interfacing the input-output, which we call a memory map input-output system, the I/O are assumed to be a part of a memory, and this is not fixed. So this is based on your settings. A memory address is assigned to the input-output device, and the use of existing address, data, and control bus in order for you to handle the I/O transaction. So in this memory map I/O, you are basically connecting your I/O to the address bus and the data bus and the control bus in order for you to handle the I/O transaction. So normally we will be in this lecture, we'll be focusing on the memory map input-output system, which assume the input-output is a part of memory and access the input-output same as accessing memory, and we need a intermediate for this interpreter, a latch to interface with the output, and buffer to interface with the input, and we'll see how to control the latch and buffer using an address decoder circuit. So in order for you to interface with an output system, normally we'll be using latch. Okay, this is an example of a latch chip, an intermediary between your output system, be it an LED or a 7-segment display and other type of output. Normally we'll be using this 74LS574, which is a latch, to interface with the output. So the pin, generally the pins look like this. We have all of this data pin, okay, data pin which connect to the data bus. Sorry, this data pin, like using it. Okay, this data pin which connect to the data bus, and then we have the output of the latch which connect to your output, basically, whether be the output is can be as an LED or 7-seg or other type of output. Okay, so the job is fairly simple. The job of a latch is fairly simple. Whatever that is being read in the data bus, the latch will output whatever in the data bus connected to it to this output pins. So that's all. That is the purpose of a latch actually. So why do we need a latch? You might ask yourself, why do we need a latch? the same reason why we need a buffer, this data bus that is connected to your 68K, so you imagine that you have your 68K here, 68K, your data bus, and then this is your lash. So this data bus over here is operating at a higher speed in the order of microseconds, micro to nanoseconds. So it is operating at high speed. So if you connect this directly to your input output, okay, there's a high probability or high chance that the data will be lost, okay, if you don't have any means of storing the data. So that is the purpose of latch and buffer, okay, latch and buffer. So that you got to remember. So this acts like an intermediary between your 68K and your input or output to store that information that is being transferred or that is being read. Okay, so that is the purpose of your buffer and latch. Okay, and then we're going to look at, okay, this is an example how you interface your latch with an LED. Okay, so you have your data bus, see, you have your data bus directly connect to the latch, and then you have your address bus connected to a decoder in order for it to select when the latch is going to be interfaced with your microprocessor. So if you remember back last time, we have looked at how to design how to interface 68K with the memory system. So we use an address bus connected to a decoder, be it a full address decoder or partial address decoder, to select the peripheral that you need to interface with the 68K. So it is the same reason here why we need a decoder. Okay, we use an address pin to select which device that you need the 68K to talk to, and most of the data is being sent over here, the data bus. So if you can see here, you have two ways of connecting a latch. Okay, because in the data bus we have the odd addressing scheme and the even addressing scheme. So this is how the way you connect it to your latch. Okay, basically this goes directly to the latch. The data pin goes directly to the latch, and then from your output here you see there's an LEDs that is connected to the latch. So by sending certain types of bits into the data bus, you can control the states of the LED using your 68K. Okay, so that's how we do it. And one thing you need to remember, again I repeat, in order for the 68K to select which output that it is talking to, we need an address decoder. So from this address decoder, this is connected to your address bus. Okay, address bus. So whenever your 68K in your programming, you are selecting those particular address, and you are moving the data to the data bus, you are basically sending information to your output. Okay, let's look at an example on how we're going to test a connection between LED and latch. Okay, so we have this LEDs. So this is the address that I mentioned just now. This address is basically an address that you specify the system to be connected to your output. Okay, so this depend on the real address system that you design. So what does this program do? Okay, starting from here, start, move byte size to D0. So this is byte size. This is written in a binary, but if you see, this is a byte size of with a value of F, and if I'm not mistaken, this is 842C, FC. Correct me if I'm wrong, but I guess this is FC. 8 plus 4 is 12, 12 plus 2 is 14. So that is A, B, C, D, E. Sorry, this is FE. This is FE. We're moving this FE to D0. So byte size. So you can imagine that at the latch side, you have 8 LED connecting to the latch. Okay, 8 LED connecting to the latch. So on. So depending on the states of this bit, okay, you will either turn on or turn off the LED. So here, I guess that 1 is you to specify the system to turn on the LED. So what does this program do? Okay, you move to D0 to the address to the data register D0, and from that data register you will move this to LED. So LED here is specified by this address. Okay, so you are moving this data to this address. So this address is connected to the latch. Okay, remember back again, this electric to connect to the latch. So branch on subroutine delay. So you have your, this will jump to a subroutine down here, delay, which is not shown, to delay the program to 1 second. And then this is to roll. Okay, to roll whatever data in the 0. Okay, so meaning that this program is actually for you to create a running light. So in this case, I imagine 0 is to turn on the LED. On the LED, 1 is to turn off the LED. So you can imagine when you do roll, it's basically you are rolling these zeros. Okay, roll, you are rolling the states of the bit. So if it starts like 1 1 1 1 1 1 0 0, the next stage, this 0 will be shifted. So you have 1 1 1 1 1 1 0 1, and so on and so on. So when this is shifted, you can see that the next one you have branch on again. So this will jump again. You move that data back to the LED and you roll it, and then you move it again. So you can imagine that your LED will be what we call as a, well, running. Okay, so you can imagine you have 8 LED. Let me denote this very. Okay, you have 8 LED. 1 2 3 4 5 6 7 8. Okay, the first one, the most left will be turned on. When the roll is executed and then it branch back to move, the second most left will be turned on, and so on and so on. So it creates like some sort of a running light pattern. So this is example on how you connect, how you can test the connection of LED to a latch. So it's fairly straightforward. Okay, and then another most commonly used output is the 7 sec output, 7 segment LED output. So I believe you have seen this before. 7 segment LED is for you to display numbers or some alphabet character. You are using this 7 LED lah for you to display numbers or character. Okay, so this is typically used in the early 80s or 90s, and I think kind of still popular now. Okay, if you want to display something, whether be it a character or numbers, you can use this 7 segment LED. So 7 segment LED, as the name implies, you have 7 segment. Okay, here you have 7 segment, and each segment is an LED. So part A, like for example, this part A is the first LED, B is the second LED, C is the third LED, D is the fourth LED, E is the fifth LED, F is this sixth LED, and lastly G is the seventh LED. So the name itself is a 7 segment LED. Okay, so sorry for the hiccup just now. So each segment is connected to an LED. It's basically represented by an LED. So depending on which LED is turned on, you can create a numbering, a numeric pattern, or an alphabet pattern on top of this 7 segment display. Okay, so example like this. So for example, the digit 0, okay, the digit 0 here. So how are we going to create a display of 0 on top of the 7 segment LED display? So if you look at this is the truth table on how you're going to create the display of 0. So starting from A, I don't know why it displays from left to right, but you can follow this through. Starting from A, if A is turned on, so imagine this is turned on, B is turned on, C is turned on, D is turned on, E is turned on, and F is turned on, you will create a display of 0 on top of the 7 segment display. Okay, so let me show you another example so you can see it clearer. Let's say we're going to display number 4 on top of the 7 segment display. So how are we going to do that? So you look at this here, you're going to set A as 0, so this part here is not light up, the LED here is not light up, but you put B as high, so this will be light up. C is 1, so this is light up. D is 0, so this is left to blank. E is also 0. F and G is 1, so F and G is 1, so you create a display of 4 on top of the 7 segment display. So the rest is fairly straightforward, fairly easy. I think if you follow through, it is the same principle of how you're going to control the 7 segment LED display in order for you to display all of the digit, the numeric character, and the alphabet character. So you can display up to 16 type of character, numeric and alphabet on top of this 7 segment display. So let's look at another example of how you're going to control the 7 segment LED display using your 68K microprocessor. So again, you have your 68K connected to to the lash. So this is connected via data bus to the lash, and then this is connected to your 7-sec LED. Yeah, so this is connected to your 7-sec LED. So 7-sec LED. Okay. So how what is this program do? Okay, what is this program does? So the purpose of this program is to display the 4 lower bit value at switch. So I imagine it, there's a switch connected to 368K as well, 4-bit switch. Imagine this is a 4-bit switch. Okay, this is a switch. You have like a 4 switch connected to your 68K. Okay, 1, 2, 3, 4. Okay, so I'm sorry, I'm bad at drawing. But depending on the value of the 4 lower bit, okay, 4 of the switch, you're going to display the value at the 7 segment. So this is what the program do. Okay, let's look at what written in the program. You have your display subroutine. Okay, you have your display subroutine here. Let's start from the top part of the program. First, okay, you already specify somewhere the address and the location of your input switch, and then what this does is it's going to put whatever value of the 4 lower bit at the switch to your data register D0. Okay, so the first what this does is just putting the value. Let's say the lower bit value, for example, just give an example of let's say that currently the switch this is off, this is on, this is on, this is off. Let's say you have 4 switch. First one just now, what I guess is off. Let's say the first one is off, the second one is on, third one is on, last one is off. This is just example. So you can imagine this to be in a binary value of 0, 1, 1, 0, which in hex value turns to 4 plus 2, 6. Okay, 0, 6. So you're moving byte size, you are moving the value of 0, 6 hexadecimal, yeah, to D0, because the switch is currently 0, 1, 1, 0. So this is equal to 6. Okay, D0. And then the next line of this program is branch on subroutine. So you're going to jump from this line to this subroutine. Okay, so what are written inside this subroutine? First, this is n intermediate word size. So this is pretty much straightforward. This is n for you. You're making an AND operation between this value and whatever is stored in D0. So this 0 just now contains your value of the switch. So this is basically for you to only to erase whatever on the top bit and to retain only on the lower bit. The nibble, the lower byte. So you remove whatever in the top byte, you only retain on the lower byte of your data. So because this is you are making an AND operation of 0, 0, 0, 1, 1, 1 with 0, 0, 0, 0, 1, 1, 0. So you whatever is in the top byte, okay, you erase it, and whatever is in the lower byte you retain it. So that's the purpose of this line over here. So next line is so this is a bit tricky. So this is a bit, you need to remember some code, okay, your move instruction. So here, move the value of code 7 into A0. So the value of code 7 here is at this address here, okay. Actually this, because in a machine language, this is a number. You specify code 7 because it's easier for you to read, but this is a number, location in the memory. At this location, you are defining a constant of this value, okay. So you imagine inside your memory space, you are defining a constant of this value. So what are these value? What are all of this value over here? 40792430. What is this value? So if you can remember just now, this value is actually the value from this table. For example, 40, at location 40 here, okay, 40, if you put it in binary format, sorry, not especially, it's 40. If you put it in binary format, let me erase here. 40 will equate to 0100 and 0000. Okay, this is 40. If you look back at this truth table, okay, the number 0 here, the number 0 here is 0 1 1 1 1 1 1. Okay, so but this is defined as 0 1 0 0 0 0. If you look carefully, this, if you inverse this bit, okay, if you inverse this bit, this will become 1 0 0 0 0 0. But because this is 7 segment LED, in the truth table it will list up to 7 digit of a binary, 7 binary digit. But if you add on the last digit to be 0, this value is equal to this value. So this value is denoted, is actually representing 0 on the 7 segment LED. Okay, this is representing 0 on the 7 segment LED. Okay, let's look at the second one, just for you to be clear. So 79 is the value of 0 1 1 1 4 2 6 7 8 9 and 1 0 0 1. But if you inverse this, you get inverse without the last bit, without the last bit. The last bit retains. Okay, you will get 0 0 0 0 0 1 1 0. So where does this located in the table? Okay, we see number 2. Okay, you see number 2, 0 0 0 0 0 1 1 0. It's the same, 0 0 0 0 1 1 0. So basically this value over here is just an inverted value of what is written in this table. Okay, what is written in the table over here is defined in this value, inverted. Why inverted? Because some latch, depending on the type of latch you use, you have a pull up or pull down type of latch. If you have a pull down, then you are controlling by not an inverted bit. But if it's a pull up, then you are controlling by an inverted bit. That's all. But the idea is still the same. Okay, so once you understand this, once you understand that the constant value that is written over this down part of the code over here represented what is in this table, then you can move on with the code. So move L hashtag code 7 to A0 is you are specifying that the address that you're putting in A0 is the address of code 7 that is inside here, is inside this memory location of code 7. There are, you already defined this constant 4079 blah 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 blah. Okay, so that's all. So means that if this location, and just give an example, if this is at 00000 is origin, for example, you start at origin, then 0001 is 40, 002 is 79, 003 is 24, and so on and so on. So you are moving only the address to A0. So next, what does this part do? Okay, this part do, what does this part do? If you remember back your move command, this is actually a type of, if I'm not mistaken, this is an indirect addressing type. Okay, indirect addressing. So what this line does is, okay, first you have a location of A0. Okay, you are going to offset the location of A0 with what is written over here. Okay, so what is written over here, and plus with what is in here. Okay, plus with D0B. So this is what it means by here, indirect addressing type. And whatever is located at this, whatever is located at this is going to be put in D0. Okay, and then you have your return from subroutine. So this will return back here. You are moving what is being put at D0 to your LED display, and then this just repeat the program. So example just now, I already forgot what's the value of this. Let's say the value of this is let me simple. Let's say that the value of switch here you are specifying as 0 3. Okay, to make this simple. So D0 here contains 03. Yeah, so you're moving the address of code 7, whatever the address code 7 may be, and then at this part A0 is the address of code 7 plus with 0, which is still the address, but in D0.B just now, D0.B is the value that what the switch is set, whatever the switch is, you set the switch at. Okay, if it's 3, then this should be 3. So when you do like this, you are specifying the address of A0 plus 0, 1, 2, 3. So you are specifying this value to be moved or insert into your D0. So 30 means that it's this part, yeah, it's this value over here, 30. Then what happens is that when you are executing this line over here, your 7 segment LED will display a 3. Okay, your 7 segment LED will display a 3. So that's how it works. So 3, how does a 3 look like in a 7 segment LED display? So you have this, 1 1 1 1 0 0 1. So 1 let me remove this for mine. So you have 1 1 1 1 0 0 1. So you will display like the number 3 on the 7 segment LED display. So depending on the switch, the value of the switch, you are telling, because this is this part here is selecting the address, the location of which value in the memory. So depending on your what number you're putting in the switch, you are displaying that particular number on the 7 segment LED display. So that's all. That is what the program does. Okay, check if I'm recording. Yes. Okay, so in the next example, this is just example of how you can use to test a connection again, but this time you are using 2 unit of 7 segment LED display. So you have 2 unit of 7 segment LED display. 2 unit of 7 segment LED display, and then you want to display that value of the failover bit inside the 7 segment LED display. So it's fairly the same with the previous program, but the only thing different, you have a stack pointer to switch from the first 7 seg to the second 7 seg. So this I left as a exercise for you to do, to understand at home. Okay, try to understand the flow of the program by yourself. This is similar with the previous program. Only thing, there's a stack pointer, or they use the concept of stack pointer to switch from one 7 seg to the other 7 seg. So that is how you are controlling the latch directly from your 68K. So another way of controlling the latch to your decoder is by using another way of controlling your output LED, 7 seg LED or whatever output you are trying to interface your 60K with, is by using a decoder or driver. Example of a decoder is 7447. You have a common anode or common cathode. Okay, you can interface your 7447 with either to a common anode 7 segment LED or to a common cathode 7 segment LED. So what's the advantage of using a decoder is, you can see here, instead of having all of the 7 pin from your latch, okay, instead of controlling all of the 7 segment LED directly from the latch, you are using only 4 pins to control one 7 segment LED. Because this decoder, it will decode whatever value on this pin, whatever value is being put on this pin in the 4-bit pin, to control the 7-bit output on this output. Okay, so for example, if let's say this is 0011, so you specify this to be 3. So what happens is that you can control the output pins of the 7447 to display a 3 on the 7 segment LED display only by using 4 pins on the input side. Okay, so normally you need all 7 pins directly connected to the latch, but now if you use a decoder, you can use only 4 pins from the latch instead of all 7 pins directly connected to the latch. So one advantage of using this is by using only a single latch. Using only a single latch, you can control up to 2 7 segment LED display. because now the pins is already reduced per 7 segment LED display. The number of pins you need to control the display is already reduced, so you can control up to 2 per lash. Okay, just now if you can see, this is another fairly straightforward program. So this display 8-bit value at switch to 2 unit 7 segment decoder 7447. So okay, let's go through this. So sorry for the stop just now. So in this example, you need to imagine that your 68K, you have your 68K, then there's a 8 switch that is connected to your 68K, and then you want to display the value on a 2 unit 7 segment via decoder. So you imagine that this is connected, your 68K is connected to a decoder, and then this in turn connected to a lash, and then this lash is finally controlling 2 7 segment LED display. Okay, you have 2 7 segment LED display. So here, depending the value of your switch, you want to display the value at the 7 segment LED display. Okay, so if you go through the this code over here, there's one cache. For example, like this, in this part, okay, you can only display the value up to 99. Meaning that the input over here, okay, the input over here, the whatever value you are specifying on the input should not exceed 99 in decimal. You are inputting in 268K in hexadecimal form, but remember that in this program, this particular program, they are only outputting on the 7 segment display in a decimal form, not hexadecimal form. So example, okay, let's say that my current input over here, I put a value of let's say a value of something that in hexadecimal that does not exceed 99. Let's say it is hex for 87. So 57. Okay, let's say my switch my switch is at position 57. That means 5 is 0 1 0 1. Okay, this is 5. 7 is 0 1 1 6 7. Okay, 1. Okay, let's say the position of the switch is like this. The first is off, the second is on, third is off, fourth is on, fifth is off, and the rest is on. So you are at this value 57. Okay, from the value of the switch, okay, just now 57, hexadecimal 57, you move this to D0. You are moving this to D0, and then you are comparing with whatever stored in D0 with 99. So if this is exceed the value of 99, you will ignore, meaning that because you have BCC here, branch and compare, will go back if this is true. If this is not, it will jump back, it will jump to this line. Okay, let me erase back whatever is written here. Okay, this will jump back to this line. So here, what the program does is the program will compare, will make an operation N of FF with D0. So this is just to delete the 3 upper byte on your whatever is in D0 lah. So imagine like currently, because this a long word size, So imagine that if let's say the value of D0 is 00000057 currently, okay, when you end it with 000000FF, when you end it with FF, you are retaining only this part. The rest, the upper 3 byte is removed because you are making the AND operation with 0 on this part here. So it means that this part is removed. You are retaining only the lower 1 byte. Okay. The next line here is you divide. So this is pretty much smart move. So remember, just now you are displaying on your 7-sec LED in a decimal number. So this 57, you need to convert it to decimal. Okay, 57, if you convert this, because this is in hexadecimal, 57 just now, if you convert this, will be 87 in a decimal form. Correct? Yeah, 87 in a decimal form. So you want to display this 87 in a decimal form. So this is one way you do it. You're using this divu command. This is divide unsigned. So when you divide unsigned with 10, the value here is 87. 87 divided by 10, you get a value of 8 with remainder 7. So inside D0, what will happen is that on the upper byte, so I'm making a highlight over here. When you use this D0, what will happen on the upper byte, you will the program will put the remainder on the upper 2 bytes. So means that the remainder here is 7, because if you calculate using your calculator, 87 divided by 10 is you get the value of 8, remainder 7. So your remainder will be 007 on the upper byte and 0008 on the lower byte. So this is the remainder, this is the quotient. So this is what is stored in D0. Okay, so and then the next line, move D0 to D1, you are copying this value to D1. So imagine this D0 is let me just quickly shows what inside the data register. So your D0 just now, is 00070008, and then you are copying this to D1. So you are copying this to D1, means that D1 is also will be the same. D1 will be the same. So 0007 0008. And then what happened when you in the next command, okay, we're done with this, swap D0, swap means that you are swapping the upper byte with the lower byte, the upper 2 byte with the lower byte. So here what happens is that because you are swapping D0, right, you are swapping D0, swap D0. So now you are swapping between this part and this part. So D0 after swap we will get 0008 with 0007. Okay, that is what happened after you swap bit. And then this is shift decimal, arithmetic shift left. So you're shifting whatever in D1 4 to the left, 4 bit to the left. So what happened in D1? So D1, because D1 is 007008. Okay, you see this command here is shifting only the byte part on D1. So what is the byte part on D1 is this part over here, the byte part over here. If I write this in binary, you will get 0, 0, 0, 1, 0, 0, 0. So if you shift this 4 to the left, 1, you are shifting all of this 4 to the left. Okay, so this one over here, if you shift 4 to the left, you will get 1, 2, 3, 4. So this part over here will end up at this part. So you will get 1, 0, 0, 0, 0, 0, 0. So meaning that in your D1, after you make an arithmetic shift left, the number is 0, 0, 0, 8, 0. Okay, and then what you do, you are going to make an OR operation on D1 and D0. So you make an OR operation between D0 and D1, OR operation. So you imagine when you OR this, both of this part, OR, yeah, whatever is OR with 0, because 7 is in the bit is 1, 0, 1, 1, 1, you OR it 0, 0, 0, 0, you will get the number by itself. Okay, this is the number by itself. So this part is 0, 0. You are all byte size, so you are only focusing on the last 2 nibble or the byte size of your number. So this is, don't care actually whatever the value is, you are only particular on this. So finally you get an output of 87, and then you move that value to an LED, which is the LED is connected to your 7-sec LED lah. So later on, you imagine in your both of your 7-sec LED, one will be making an 8 display, another one will be making a 7 display. So 8, 7, yeah. So but remember, the input here is in hexadecimal. Okay, hexadecimal. So this is how you display a hexadecimal 8-bit value to 2 unit 7 segment via decoder 7447. So another thing that you need to remember is that compared to the previous program, you need to specify the value from a truth table that correspond to the value of the 7 segment LED display you want to put. This part you don't need to make that definition, because why? Because our decoder here takes a direct value, direct decimal value to display on the 7 segment LED. So there's a pretty much smart way to display. Okay, let's look at the next part of this lecture on buffer. So buffer, similar to latch, whatever it is in connected to the input, it will display on, it will put on the output. So this part of output over here is connected to your data bus on your 68K. So how you're going to interface it with your 68K? So you have your buffer. You have your buffer connected to the data bus on your microprocessor. Then again, you have your decoder for it to select to put the buffer on a on state. Okay, and then this is how you connect it to your 68K. So this is your input side. This is your connected to your data bus. Okay, this is connected to your data bus. So whatever is being turned on, let's say this is 10001000, that value will be put on your data bus. So again, why do you need buffer? Is because the data bus operate at high speed. So when things are operating at a high speed, the possibility of losing some information is high. Okay, so you might not be able to cache whatever is being inputted. So that's why you need buffer to retain to retain the information on your input. That's the function of a buffer. So this is example. Okay, actually this is an example of the next program over here. So in this program, okay, so how are you going to use your 68K to take an input which is connected to a buffer and display it on LED? So first you need to specify an address where is your input is connected. Okay, this is important. So for example, in this particular example, you are specifying the switch is connected to 8001 and your LED is connected to A001, and then you start with your main program. So it's pretty much simple program. This is the origin of your program. Move byte size whatever is at the switch to the LED, and you branch, you repeat the same process again and again and again. So whatever is being put on your switch, you will display to LED. So in this case, for example, like this is an example if you want to control directly without using a microprocessor, right? But if you are using computer, this is connected to your buffer, and then this really connected to your 68K. So what the program does, when you turn on the switch, the computer will read from the buffer, and then it will put whatever state of the switch on top onto your LED. So that's all, pretty easy. Okay, I think that's all for today. In the next part of the series, we'll be looking at parallel interfaces. This will be, I guess, towards the end of this course. So thank you very much, and I will see you next time.